Good evening, everyone. Welcome to week 7 of live problem solving on GATE Metallurgical Engineering. I am Santhya Krishnan P, and these sessions are brought to you in association with NPTEL and PMRF. So, for the past 6 weeks, we have been solving several questions on GATE Metallurgical Engineering, and I've come to notice that the students usually join very late for the sessions. So, please do join the sessions exactly at 6 p.m. So, that is a request from my side to all of you. And so far, we have been solving problems from previous year questions in GATE Metallurgical Engineering. And since GATE is approaching fast, like in 1.5 or 2 months, I request that all of you thoroughly solve problems now on. And people who are planning to take the GATE examination this coming year, please do focus on such problem solving sessions. It's going to help you in the long run. So I hope you have gone through the previous videos that we have uploaded. On that note, let me move on to today's sessions. So the first question today is, match the following fracture surface features listed in group 1 with the fracture mechanisms listed in group 2. So in group 1 we have striations, dimples and microvoids, flat facets and river markings, jagged surface with grain-like features. And in group 2, we have intergranular fracture, cleavage fracture, ductile fracture, and fatigue fracture. So in group 1, we have how the fracture surface or the fractograph looks. And here we have the type of fracture that could be associated with group 1. So the thing is to match whatever fracture is there in group 1 to the fracture features present in group 1. So first we will see what happens in ductile fracture. So, in case of ductile fracture under tension, that is a ductile specimen, and that specimen that is capable of undergoing elastic and plastic deformation, that is under capable of elongating, is being stretched, that is, it is being subjected to tension. So, then what happens if we observe macroscopically, we will be able to see such a cup and cone like feature, and this particular edge is known as a lip. It will be protruding outside. So this is the cup and cone feature that is found macroscopically around the fracture surface. And if we observe this particular session under a microscope, we will be able to see dimples or cup-like depressions. These dimples or cup-like depressions are usually formed due to microvoid coalescence, that is, small voids in micron level will be coalescing with each other to form these dimples. And deeper dimples means that it is a material having higher ductility. So in case of ductile fracture under tension, there are two types of fracture. One is transgranular and one is intergranular. And as the name suggests, transgranular means it will be happening across the grains, and intergranular means it will be occurring between the grains. So if we see a transgranular ductile fracture, we will be having such kind of a sponge-like image can be observed here. See, these dimples are there, microvoids, coalescence is there, and such an image could be obtained. But if we see the intergranular ductile fracture, the dimples will be there, but the dimples will be more or less in the form of a grainy appearance. So that is the difference between transgranular and intergranular ductile fracture. And suppose we are subjecting the material to torsion or twisting failure, dimples can be observed, but we should be seeing that these dimples are elongated, or also these are known as skewed dimples. So that is what happens in case of ductile fracture in tension and torsion failure. Now we'll move on. Now we'll see brittle fracture in tension. That is a brittle material, a material that is not capable of elongating is being pulled apart. So in that case, if we see macroscopically, we won't be able to see something like a cup and cone feature or something. It will be a very flat surface and it will be perpendicular to the applied load. And in brittle failure in tension also, there is transgranular, intergranular brittle fracture. Transgranular fracture or cleavage fracture, what happens is that riverbed pattern can be observed under the microscope. And if we see in case of an intergranular brittle fracture, there will be decohesion, that is separating of the grain boundaries, and it will have a grainy appearance, a square or somewhat of an rectangular or square shaped grains can be observed. And also such a material surface will have chevron marks. Chevron marks means these VV kind of markings will be there on the surface. So why do these have these marks? This will help us in assessing the direction of crack propagation as well as the point at which the crack had initially originated. So that is the brittle fracture failure in tension. So now we have fatigue failure. Fatigue failure occurs when a material is subjected to a constant load for a prolonged period of time, for a particular load for a prolonged period of time. So in such cases, there will be progression marks or beach marks that will be present. Progression marks or beach marks is there. So here is the fast fracture region, and this is the place where the fracture initiated. Then we have fatigue crack due to the propagation. And if we see, we will be having such kind of striations or breach marks. And if we observe macroscopically, we will be having ratchet marks. That ratchet mark will be at the boundary between two failure planes. And if we see, this will be having multiple fatigue striations, and each of the striation is representing a stress cycle that was experienced by the part. So that is what happens in fatigue failure. Now that we have seen all those, so we can start matching. So striations, as we just discussed, it comes with fatigue failure. So B will go with 4. Dimples and microvoids we had discussed in the first case, that occurs in case of what kind of failure? Ductile failure, and ductile fracture. Therefore, Q will be 3. Next is flat facets and a river marking. So we can understand flat facets means that it will be brittle fracture. In brittle fracture, a river marking means that it will be the case of intergranular cleavage fracture. And a jagged surface with green-like features means that it will be intergranular fracture. So P will be 4, Q will be 3, flat facets and river markings will be 2, jagged surface with green-like features will be intergranular fracture. So we can say that the option will be P4, Q3, R2 and S1. So that is option C. So in case of match the following questions, please note that if you know approximately 2 to 3 answers, it is most probable that you need not be very sure about the fourth option. So in this case, we know that striations are form of fatigue failure. So in this case, B is surely 4. So if you know that very surely, there is no need of even seeing the other 4 options, because P4 is only found in option C. That is the case. But if you know Q is 3, there is a possibility of 2 options being right. So that is the case. So try to match as many number as possible, and then try to compare them with the options. So that is the most practical way of doing match the following answers. So I hope all of you are clear with these questions. Now we will move on to the next question. Determine the correctness or otherwise of the following assertion and reason. Assertion, so it was asked in GATE Metallurgical Engineering 2014 for 2 marks. So and copper aluminium phase diagram related question or alloy related questions are commonly found. So please be clear with these concepts. So the assertion here is peak aging time for an aluminium 4 weight percentage copper alloy is indicated by a maximum in hardness. And they are telling that the reason for this is maximum volume fraction of theta precipitates is formed at the peak aging time. So we have 4 options A, B, C and D. Either A and B are true, A is true, B is false, or both are false. So we need to justify how we are telling whether the assertion is true or false, or whether the reason is true or false, or both are false or both are true. So for that, we need to understand the theory that is associated with precipitation hardening in case of aluminium copper alloys. So Phase hardening in aluminium copper alloy. So precipitation hardening in aluminium copper alloy. So we have the aluminium copper phase diagram here. So for an aluminium copper alloy, initially we will be heating the material to a point, we'll be heating the alloy to a point M, so that it will be a homogeneous, a single phase alpha alloy will be there. From point M, it will be quenched to a point F, and F is in a region where there is alpha as well as there is the CuAl2 precipitate. But we need to understand that the CuAl2 precipitate is not immediately formed as we have it at point F. Slowly, when we are heating the material from F to N, a number of stages will be passed, after which finally we will be getting the alpha plus CuAl2 precipitate. So upon quenching the alloy from the solid solution, the copper atoms will start coming together and they will start nucleating homogeneously to form what are known as Gunnier-Preston zones or GP zones. And it is, we have to note that these GP zones are coherent with the lattice of the ALCU system. Then what happens? Some of the GP zones will start growing and a three-dimensional precipitate starts forming. And this precipitate is called theta double prime. These theta double prime precipitates can catch the copper atoms more efficiently than the GP zones, and also we have to note that these theta double prime precipitates are also coherent. Then, as time passes, heterogeneous nucleation starts taking place. Usually, heterogeneous nucleation takes place at defects, especially dislocations and so. And what happens? More fully coherent precipitates start forming, and these are known as theta prime precipitates. Still, we have not reached the final CuAl2. So, initially we had GP zones, then theta double prime, then theta prime, and we are going towards the fully three dimensional precipitate. And as time goes on, the final CuAl2 or theta precipitate will start nucleating at the grain boundaries and at the theta prime precipitates. These precipitates are fully three-dimensional in nature and they are coherent with the lattice. And as the incoherent with the lattice, and as the incoherency increase, this precipitates gains the ability to strengthen the material. Therefore, if we see the plot of yield strength or hardness versus the log of aging time, so initially GP zones are formed, not much hardening is taking place, but as we move from theta double prime to theta prime and finally theta, there will be a particular point where maximum aging, or we can say maximum hardness, occurs. It is usually said at being of the theta prime precipitate. So that is what happens during the age hardening in case of aluminum copper alloys. So, our question is, first assertion is peak aging time for aluminum 4 weight percentage copper is indicated by a maximum in the hardness. So, the assertion is true. So, peak aging time means the peak aging time, that is the most required. The peak aging time is indicated. After the peak aging time, it goes to a state of overaging, that is the hardness starts decreasing. So the peak aging is denoted by a maximum in hardness or the yield strength. So the assertion is true. So the reason for this, the maximum volume fraction of theta precipitates is formed at the peak aging time. But we have to see theta is here. That is not the peak hardness or the peak aging time. It is somewhere between theta double prime and theta prime, and usually we say that the peak aging occurs for the theta prime precipitates. Therefore, the reason for this is false. The maximum volume fraction of theta precipitate is formed at peak aging time is false. If it was instead given theta prime, this would also have been true. Therefore, A or the assertion is true, R or the reason is false. A is true, but R is false. Therefore, the answer to this question is option A. I hope all of you are clear with the assertion reasoning question in case of aluminum copper alloys. We had similarly solved an aluminum copper alloy question in the previous class. I hope in case you have any doubts, you can go through those videos, and even if the concept is then also not clear, you can mail me and I'll be able to help you through it. So the next question is, identify the type of the following invariant reaction. It was asked in GATE Metallurgical Engineering 2014 for 1 mark. So we know that there are invariant reactions. So how do these invariant reactions come about? We know that the number of degrees of freedom, or the number of phases that can coexist in a phase diagram at equilibrium, is given by the Gibbs phase rule. What is the Gibbs phase rule? F plus P is equal to C plus N, where F is the number of degrees of freedom, P is the number of phases present, C is the components present in the system, and N is the number of non-compositional variables. And F, we have told that it is the number of degrees of freedom, right? So what is this number of degrees of freedom? It gives us the number of parameters that we can change independently without altering the state of the system. So when F is equal to 0, it means that if we change any parameter, either temperature or composition, the system will change to a new phase. So when F is equal to 0 in a binary system, we can call it as an invariant reaction. That is, if we change either the temperature or the composition, we will enter into a new phase. Those are known as invariant reactions. So the invariant reactions can be seen in iron carbide diagram. So there are multiple invariant reactions. There is the eutectic invariant reaction, where a liquid will reversibly change its phase into two solids. So in case of a phase diagram, at this point the liquid will change to alpha plus beta, or we can say when we're increasing the temperature, alpha plus beta suddenly changes into liquid at this point. So we cannot move either horizontally or vertically without changing. So if you move from this point, it will change to a new phase. If you move from this point, it will change to a new phase. That is the invariant reaction. F will be equal to 0 in that case. And we have eutectoid, where a solid will change into two another solids. And we should remember that whenever there is an oid present, it will always be composed of three solids only. In case of peritectic, one liquid and alpha will together change into another solid. In case of peritectoid, two solids will reversibly change into the third solid phase. That is, alpha plus beta will change into gamma, or gamma can change into alpha plus beta. Then we have metatectic and monotectic. In case of metatectic, alpha becomes liquid plus beta. And in case of monotectic, liquid 1 becomes liquid 2 plus alpha. So examples for each of these are also given here. For example, eutectic, we have the silver copper one. Then we have the lead tin system. Eutectoid, we have the iron carbon diagram. Peritectic, we have copper zinc. Peritectoid also can be seen in copper zinc diagram. Metatectic and monotectic in UMN and CUPB respectively. That is uranium, manganese and copper lead plummet respectively. So that is what we can see in case of invariant reactions and invariant points. So our question is, liquid 1 plus solid 1 gives solid 2. So L1 plus S1 gives S2. L1 plus S1 gives S2. So where is it? L1 plus S1 gives S2. So it will be a peritectic reaction. So at least all these four options you have, metatectic and monotectic are not that important compared to these four that we have given in the option, that is eutectic, eutectoid, peritectic and peritectoid. I would suggest that people be comfortable with answering questions related to at least these four. There are other invariant reactions like monotectic, metathetic, syntectic and all, but those are less asked compared to the eutectic, eutectoid, peritectic and peritectoid reaction. So please familiarize with the equation. So a liquid 1 plus solid 1 can be solid 2, or they can give us L plus alpha reversible beta. So these notations also please familiarize yourself. I hope this question is clear to all of you. Now we'll move on to the last question of today. In an exemplary powder pattern of a simple cubic crystal or a primitive cubic crystal, the second peak corresponds to dash. It was asked in GATE Metallurgical Engineering 2015 for 1 mark. So if we can see here, this is a table which gives us the allowed reflections and forbidden reflections in XRD patterns. These are arrived based on extinction rules. So based on the extinction rules, it will help us in understanding. Suppose our material is having a primitive unit cell. What are the allowed reflections? Any H scale combinations are possible. In case it is a BCC, there is a condition that H plus K plus L should be an even number. In case of face centered, it should be either all odd or all even. So based on the extinction rules, we can find out the allowed reflections and forbidden reflection. So please be familiar with primitive body centered and face centered, and if possible FCC diamond and HCP. So more than FCC diamond, I would say HCP would be important. So if you know primitive or simple cubic unit cell, allowed reflections mean any combination of HKL is possible, and there is no restrictions on forbidden. Any peak can be observed in a simple cubic crystal. And also, we should also keep in mind that in case of HKL value, 0 is considered as an even number. Please note that also. So the first peak will be what any HKL is possible. So it can't be 0, 0, 0, right? Therefore, we can say first peak will be 1, 0, 0. If the first peak is 1, 0, 0, what will be the second peak? First second peak will be, we are replacing this 0 also with 1. The second peak will be 1, 1, 0. So that is the case here. So in case any combination of HKL values, either odd, even, mixed, anything is possible. So the first peak will occur at 100 and the second peak will occur at 110. So this is the answer to this particular question. Therefore, the answer is option D, 110. So please familiarize yourself with this table where we can find out the HKL combination of primitive, body centered and face centered. So I hope this question is clear to all of you. I also hope that all the questions that we have discussed so far is clear to all of you. In case you have any doubts, please do email me at santra.pmrf@gmail.com, and also please attend the classes sharply at 6 p.m. Do not come at 6:15 or 6:20 and then it will be difficult for both of us. So I request all of you to go through all these videos and be present for the classes sharply at 6 p.m. So thank you for your kind attention and I hope to see you next week. Thank you so much.